Welcome all of you. As far as today's class is concerned, today we are going to discuss an important concept of dynamics, that is velocity measurement or acceleration measurement, or the motion analysis of a rigid body in two different frames of reference. What do we understand by the two frames of reference? In order to make you understand what is the central idea of this topic, I just need to introduce you to the problem 16.20. We will not be solving this problem right now because we have not understood the formulas or the equations which we have to use in these types of questions, but we need to understand what we have to learn in this topic. If you look at the question says planes A and B. There are two planes. There is plane A and there is plane B. Okay, this is an aircraft A, plane A, and this is an aircraft B. Okay, so we are having two aircrafts, plane A and plane B, fly at same elevation. They are flying at the same elevation. We mean to say they are flying at the same altitude as shown in the figure. This is the top view when these two planes are being viewed from the top. If you see from the ground, then we can see something like this. We'll be having aircraft A flying like this. This is our aircraft A. And we'll be having aircraft B. We'll be having aircraft B like this. Okay, we have aircraft B like this. They are at the same elevation from the ground. They're at the same elevation from the ground. That is, as far as plane A is concerned, on the plane A is at some elevation from the ground, at some height from the ground. Let's say that plane A is at a height h from the ground. Now, on the right hand side of the plane A, there is plane B. Okay, this is not below point plane A. This is on the right hand side of plane A. That is that, as you can see here. This aircraft A is flying in this direction. This aircraft A is flying in this direction. On the right hand side of plane A, you are having plane B. So plane B is flying on the right hand side of plane A. And these both planes have same height from the ground. Their elevation from the ground is same. Now the question says, determine the velocity and acceleration of A. What is the velocity and acceleration of A as measured by the pilot B, as is measured by the pilot B? That is, the question is like, we are having two aircrafts, aircraft A and aircraft B, and we are being given the information that aircraft A is flying at a speed of 700 km per hour and aircraft B is flying at a speed of 600 km per hour. When we are given information that an aircraft A is flying at a speed of 700 km per hour, this is the velocity of the aircraft as measured by an observer on the ground. Because the observer on the ground is at rest with respect to the aircraft A, and the aircraft A is giving us and the person on the ground is giving us the information that the aircraft A is flying with a speed of 700 km per hour. So we say this 700 km per hour, this is the velocity of aircraft A as measured by an observer on the ground. Okay, we say there is a ground observer, there is an observer on the ground, there's a ground frame of reference. This is x-axis with respect to that ground observer, this is y-axis with respect to the ground observer, this is z-axis with respect to the ground observer. And the ground observer observes the motion of aircraft A and says it is flying with a speed of 700 km per hour. So this is the speed of aircraft A is as measured by an observer on the ground. So this is velocity of A with respect to observer on the ground. G. In the same way, it is being said that aircraft B is moving with a speed of 600 km per hour. This is the velocity of aircraft B with respect to an observer on the ground. This is very important. Though this book is not explicitly telling us this 600 km and 700 km per hour are the velocities of aircraft B with respect to ground or the velocity of A with respect to ground respectively, but we know that whenever it is being said that an aircraft or a car is moving with a speed of x kilometer per hour or x meters per second, it's the velocity of that vehicle with respect to the ground, otherwise not specified. In the same way, when it said it's 700 km per hour, it simply means it's with respect to the ground. This is 600 kilometer per hour. This is with respect to the ground. Then the question says, determine the velocity and acceleration of A as measured by B. What we have to do? Now, as these two aircrafts are flying at the same altitude, on the right hand side of aircraft A, we are having aircraft B. Okay. So if we ask pilot B, who is on your left hand side, pilot B will say that I am having aircraft A on my left hand side. Now we will question this pilot in aircraft B. We will tell this pilot in aircraft B, what is the velocity of the aircraft A with respect to you? That is, what is the velocity of A? What is the velocity of A with respect to you? That is, what is the velocity of aircraft A with respect to an observer in aircraft B? This is velocity of A with respect to B. We have to find this, okay? Apart from finding this, what we have to find, we have to find acceleration as well. That is, we have to find the acceleration of A with respect to an observer in aircraft B. These two things we have to find out. Again, I repeat, as far as the values given to us are like this aircraft is moving forward with a speed of 700 kilometer per hour and its acceleration is 50 kilometer per hour square. This aircraft B is moving forward with a velocity of 100 kilometer per is moving with a speed of it's moving with a speed of 600 kilometer per hour and its acceleration is 100 kilometer per hour square. The values of acceleration and velocities for both aircrafts are given to us, and these are given with respect to a frame of reference. That's what we call as a ground frame of reference. These velocity and acceleration measures are with respect to the ground frame of reference. But what we have to find? We have to find the velocity of aircraft A as measured by an observer in aircraft B. We have to find out the acceleration of aircraft A as measured by an observer in aircraft B. These are two important things. So what we are given the velocity of A with respect to one frame of reference, but we have to calculate the velocity or acceleration of aircraft in another frame of reference. If you look at this overall problem, in this overall problem, we have to find velocity of A with respect to B. So we have two frames of reference. We are having a ground frame of reference, okay? So this is our ground frame of reference. This, with respect to ground, with respect to this ground, this B is, if we draw a vector, if we draw the vector, with respect to the ground, aircraft B is moving, and with respect to, so if we have an observer on the ground, this is ground frame of reference, this is origin with respect to the ground frame of reference. The person on the ground will say that aircraft B is moving, okay? It will also say that I'm observing that aircraft A is also moving, okay? Aircraft A is also moving. So this is with respect to the ground. The observer on the ground is observing that aircraft B is moving, aircraft A is moving. So this is our one frame of reference. Another frame of reference is our B frame of reference or A frame of reference. Since we have to observe the motion of A, we have to find the velocity and acceleration of A with respect to B. Therefore, B becomes another frame of reference for us. So this B is another frame of reference. We will be calling this B as beta. This is another frame of reference. So what we have to calculate, we have to calculate the velocity of A with respect to B. We have to calculate the velocity of A. We have to calculate the velocity of A and acceleration of A with respect to B. When we are given velocity and acceleration of A with respect to ground, we are given velocity of A with respect to ground, acceleration of A with respect to ground. We are given velocity of B with respect to ground, acceleration of B with respect to ground. Now what we have to calculate? We have to calculate the velocity and acceleration of A with respect to frame B, with respect to an observer in B. How we do it? There are two parts of dealing with this type of problem as far as our lecture plan is concerned. First and foremost, like in previous acceleration and velocity analysis, we have first derived the velocity and acceleration equations, then we have applied them. But here, what I will be doing, I will not derive the equations, the velocity and acceleration equations. I will not derive them, but I will simply present them to the students. What are the equations for calculating the velocity and acceleration of a body? in a moving frame of reference, when the velocity and acceleration of the moving frame of reference with respect to the ground frame of reference are given. It is like we have this A is our A. We are having in ground frame, we are having observer. Let me just make these. This is our observer in ground. This is our observer on ground. This is one. This is our observer on ground. As far as this B is concerned, this B is nothing. This beta is our moving frame of reference, okay, because this is moving, so we call this as moving frame of reference. As far as the ground frame of reference is concerned, that is this ground frame of reference is at rest, so we are having moving frame of reference, and this is the object which we have to, whose acceleration and velocity we have. Fine, this is our object, or this is what we can call, say this is the body, this is the rigid body whose velocity and acceleration we have. Fine. Now, as I was saying right now, that we have two ways of, we have two parts of our lecture schedule for this. I have divided the lecture into two parts. First one is the derivation. What is the velocity? What is the equation for acceleration and velocity of an object or a body with respect to a moving frame of reference? Okay. When we are given the velocity and acceleration of the object with respect to the ground frame of reference, this is the equation needs to be derived. This is the first portion of my lecture, but I will not be deriving it right now. I will be first of all introducing you to the velocity and acceleration equations and how to use them in solving these problems. As we will go in the three-dimensional kinematics of rigid bodies, again we have to encounter problems in moving frames of reference, but the problems will be in three dimensions. Okay, there will be space problems. There I will be deriving the velocity and acceleration equations for moving frame of reference in three dimensions. There we will derive them. So I can skip the derivation portion for some time. Let me directly write the equations and help students and introduce students the equations, and vis-a-vis make students help students or introduce to students how to use these equations in solving the problems. Okay, and in the three-dimensional kinematics of rigid body, that's a chapter coming up within 5 days, I will be deriving the equations. By that time, the students will be acquainted in using the equations, and the derivation portion will become easy for us. Now, let's get introduced to the equations. Which type of equations we have to use in solving these types of problems? Okay. So the type of problems we have, in these types of problems, we can now see we have a ground frame of reference. So we have an observer on ground. We call this as, this is ground frame of reference. We call that, we represent it. This is our ground frame of reference. This is one frame of reference. Okay. This is the origin of this ground frame of reference. Let's write this as O. We have another frame of reference. We have another frame of reference. As is here, we had a ground frame of reference that was giving us information about A and B. And then we have another frame of reference that was B. Okay. So we represent this another frame of reference, moving frame of reference by beta. And let's suppose the origin of the frame of reference is at a point, we call that as O prime. Okay. Now let's suppose both an observer, we have two observers, observer in a ground frame of reference and an observer in a moving frame of reference. So I will write, so this is ground frame of reference and this is moving frame of reference. Okay, this is moving frame of reference. So we are having an observer in a ground frame of reference and we have an observer in moving frame of reference, and both these two observers are observing the motion of a rigid body, and let's call that rigid body as, represent that position of the rigid body by P, as we are representing this rigid body by point A. Okay, this is just a symbol. Okay, point P. So now point P is a rigid body. This is the rigid body. This is the rigid body is represented by P. Okay, P. The point P represents the rigid body, and this rigid body motion is being observed by an observer on the ground as well as another moving frame of reference. So let's draw the vectors. Let me draw the vector from ground frame of reference to P, and let's call this vector as, we call this as, this is the vector, position vector, drawn from, this is the position vector drawn from an origin of the ground frame of reference to point P, ROP. This is our vector. Let's draw one more vector, and this vector we draw from O to O dash. This vector is the position vector drawn from an observer in the ground frame of reference to an observer in the moving frame of reference. I will write this as this is from O to O prime. This is vector. And we also draw the vector since P is also being observed by an observer in moving frame of reference. So we will draw a vector from O to P. And we write this vector as, this vector is position vector drawn from O dash to P, or O dash P. Okay, this is. So this diagram is very important diagram. In fact, if students can apply the triangular and can in fact derive the velocity equation themselves, but let me postpone that for some time and let me simply write down the expression. Okay, so the expression will be, see, this is important. The expression is, I will return back to this diagram in three-dimensional kinematics. Okay, when I will be deriving the expression. Till then, I will simply write it, and the expression is velocity of P with respect to the ground frame of reference. It's written like this. So I write here, velocity of P, or let me write it here. Then we write, the expression is velocity of P with respect to ground frame of reference. It's written as velocity of P with respect to ground frame of reference is equal to velocity of P with respect to moving frame of reference. That is velocity of P with respect to moving frame of reference, which we are presenting by beta, plus velocity of moving frame of reference with respect to ground frame of reference. That is velocity of O dash with respect O. Okay, we can write velocity of B beta with respect to G. Okay, so we can also write this is velocity of, or we write velocity of O dash, velocity of the origin of the moving frame of reference with respect to the ground frame of reference, plus angular velocity of the vector drawn from O to O dash. That is omega angular velocity of the vector drawn from O to O dash, and its cross product with, when we write angular velocity of O dash with respect to O, when we write this is angular velocity of the vector drawn from O dash to O, which is simply the angular velocity. See, as this body is having planar motion, then that simply means angular velocity of O dash vector simply means angular velocity of the rigid body. Angular velocity of the frame of reference beta, omega beta. Okay, so in place of this omega O dash, we can also write omega beta. That I will write in the next expression. Oh, okay. The cross product with the radius vector drawn to point P, the radius vector drawn to the rigid body from the moving frame of reference. That is R O dash P. This is the expression for the velocity. We will derive it in three-dimensional kinematics. Here we just need to use it only. So we can further modify this equation. We can write the velocity of P with respect to the ground frame of reference, velocity of P with respect to the ground frame of reference is equal to velocity of P with respect to the moving frame of reference, that is beta, plus velocity of O dash, origin of the moving frame of reference with respect to the ground, that is velocity of O dash with respect to ground, plus angular velocity of the vector o dash. The angular velocity of the vector o dash is nothing. It can also be represented as, this is angular velocity of the rigid body beta, and its cross product with r o dash p. That is r from o dash to p. This is the expression for velocity. Okay, it is this expression. It is this expressions. Both these expressions are same. We will be using these expressions for finding the velocity of A with respect to the velocity of B. Okay, this is one. Second expression is about the acceleration. Okay, if we have to calculate the acceleration of P with respect to the ground, when we are given, or we have to calculate the acceleration of P with respect to beta, when we are given the acceleration of P with respect to the ground, as is the case. We are given acceleration of A with respect to ground. We have to calculate acceleration of A with respect to B. Okay. So how we will do it? The expression for the acceleration is, this is very important. As far as the acceleration equation is concerned, the expression for the acceleration is, it's written as, very important, acceleration of P with respect to ground frame of reference. It's written as acceleration of P with respect to ground frame of reference is equal to acceleration of P with respect to ground frame of reference is equal to acceleration of P with respect to beta. It's written as acceleration of P with respect to moving frame of reference. Acceleration of P with respect to moving frame of reference. That is here. Acceleration of aircraft A with respect to ground is equal to acceleration of aircraft A with respect to aircraft B. That's what we are writing. Acceleration with respect to plus acceleration of O dash with respect to O. Acceleration of O dash, origin of the moving frame of reference, with respect to ground. Acceleration of O dash with respect to ground, plus angular acceleration of beta with respect to ground. That is angular acceleration of beta. We write this as angular acceleration of beta. We write this as alpha of beta. Angular acceleration of beta cross radius vector drawn from O dash to P. We write this as R O dash to P. A radius vector drawn from O dash to P minus angular velocity of beta, that is omega beta, on angular velocity of beta square, and multiplied by radius vector from O dash to P, R O dash P vector. This expression plus 2 times angular velocity of beta vector cross product with velocity of P with respect to beta. This is the expression. Cross product with velocity of P with respect to beta. This expression is the expression for calculating the acceleration. Okay, this gives us the relation of acceleration of a rigid body between two frames of reference. One is a moving frame of reference, another is a ground frame of reference. I'm reminding my students that we have not derived this equation yet. First of all, these equations are a bit lengthy and a bit because of their length and because of so many vector equations in them, they are become very laborious for the students to use in few first problems. In first 3 or 4 problems, at least in first 3 problems, the students really get, the students really face some sort of difficulty in using these equations. But after 3 equations, after solving 3 problems, I have myself noticed it that students excel in using these equations. Once you excel in using these equations and you get used, students get used to the terms and the vector forms of these equations, then the derivation becomes easy. Okay, so this is what the lecture schedule is all about. First of all, introduce these two equations to the students. I have introduced the velocity equation and the acceleration equation. Now we will be using this velocity and acceleration equation in solving the problems. Once we solve the acceleration and velocity problems using these equations, then in three-dimensional kinematics of rigid bodies, we will also derive them. The question is, from where we have obtained these expressions? Yes, we will explain that in kinematics. In this lecture, we will just make use of them. As far as this term is concerned, this is a very, very important term. We'll be calling this as, this term is a famous term in mechanics. This is called Coriolis acceleration. This is called Coriolis acceleration. Coriolis acceleration. Okay, so sometimes we are asked even in gate examinations, we are given questions wherein we simply have to calculate the Coriolis acceleration. It's 2 times angular velocity of the moving frame of reference and its cross product with velocity of the rigid body with respect to the moving frame of reference. This is called Coriolis term or Coriolis acceleration. Now, after writing these two equations and understanding each and every term, let's now try to apply these equations. Let's apply these equations in solving the problems, and that we'll be doing in the coming up lectures. So thanks for today.